A proton moves along the positive x-axis with a velocity of 1.0 times 10 to the 7th meters per second. As it passes the origin, what is the magnetic field at the following points? This is the second part of our solution to part B of this example, in which we have to determine the magnetic field on the y-axis. In this second part, we're doing an alternative to using the right-hand rule for finding the direction of the magnetic field. We're going to use the actual definition of the cross product to find the direction of the magnetic field. So for this example, we use the right-hand rule to determine the direction of the magnetic field at point B due to that charge moving along the positive x-axis as it passes the origin. But we didn't have to use the right-hand rule. We could also find the direction of the magnetic field, or find the magnetic field with the direction built into it, by just going back to the cross product. So let's redo this problem by just using the cross product. So in redoing this problem, we know that the magnetic field at point B is equal to mu naught over 4 pi, the value of the source charge, V cross R, the cross product between the velocity and the unit vector representing the relative position of our point in space, and this point is point B, over R sub B squared. Now remember, we called R sub B, we said that that is in the positive y direction. And we have the velocity vector in the positive x direction, where the magnitude of the velocity, or the speed, was just given as 1.0 times 10 to the 7th meters per second. So we need to find the cross product between the velocity vector and the unit vector representing the relative position between the point and the source charge. Now, quite simply, the unit vector is just along the y-axis, but let's go ahead and quickly show that. So the unit vector is equal to that our vector over the magnitude of our vector, where our vector is a j hat. The magnitude of this vector is a, so the unit vector is along the y-axis, j hat. Well, now let's use this to evaluate the cross product between our velocity vector and the unit vector. I'm going to use a 5x3 matrix to determine the result of this cross product. We've discussed this in our Physics 4a class, at least if you've taken Physics 4a from me. So the second row will correspond to the components of velocity. The third row will correspond to the components of our unit vector. And we are going to take the set of diagonals, I hat, j hat, and k hat, and we're going to subtract from the other direction, k hat, I hat, and j hat. And when we evaluate this cross product, notice what we have. We have that our cross product of those two, of the velocity vector and the unit vector, this should have been a unit vector here, the cross product between our velocity vector and the unit vector of our relative position ends up being equal to v k hat. So the magnetic field at point B is equal to mu naught over 4 pi q the cross product between v and the unit vector, which we just found to be v k hat, over r sub b squared. Now this is just mu naught q v over 4 pi a squared k hat. And if you remember, this is exactly what we got before. The exact same expression means that the magnetic field at point B is equal to 1.6 times 10 to the minus 13 Teslas in the positive z direction. And so the point here is we were able to use either the right-hand rule to find the direction of our magnetic field, or stick to the cross product to find the direction of the magnetic field. Either way, as long as we are consistent, we're going to get the same result. Now, the right-hand rule is convenient when you have things that are in the coordinate planes, like the xy plane, the yz plane, or the xz plane. Not so convenient if your object isn't moving in a plane or your point isn't in one of the planes relative to the object's line of velocity. And so sometimes using the unit vector version, or if you're given unit vectors for the velocity and the relative position, using the cross product version of the Biot-Savart law, I would say, is the way to go. But if you're given a set of quantities that are in the planes, like the velocity here was in the xy plane, the relative position of all of the points were in the xy plane. Because of that, it is very easy to use the right-hand rule to determine the magnetic field.